Hi everyone, Ms. Kilroy here. Today you're going to be taking notes on the periodic table. So just a reminder how to set up your notebook. You've already glued in your pages. This is starting on page 46. The title is the periodic table. Essential question is, how is the periodic table arranged or organized? Have a notes and questions section and then a summary at the bottom. Page 47, you glued down your periodic table in the center of the page. And then page 48, same setup, C-note style. And remember, you can pause this at any time or go back to it in case you miss something. So if I'm going too fast, you can pause. All right, here we go on our notes. So how was the periodic table discovered or arranged? So it started with this guy named Dmitri Mendeleev in the 1860s. And he discovered a pattern to the properties of the elements. So he arranged the elements by increasing atomic mass. So remember, that number is a number on the bottom. So he organized it by the number on the bottom, the mass of the atom. And then from that, once he laid out all of his note cards and he put them in order, see how they get bigger, of increasing atomic mass, he could predict the missing elements and their properties, so like their characteristics, what they were like, just based upon what the ones around it were like. So Mendeleev organized the table by atomic mass. The next guy about, that was in the 1860s, this is 1914, so about 50 years later, Henry Moseley determined the atomic number of atoms. And so he rearranged the elements by increasing atomic number. So remember, that's the number at the top, or the number of protons. So you can see it increases as we go from left to right. So the periodic law says the chemical and physical properties of elements are periodic functions of their atomic number. So basically what that's saying is the element and what its characteristics are based upon the number of protons, or the atomic number. All right, so just breaking down the periodic table, we've got our periodic square, and the chemical symbol is the abbreviation of the element. So for example, a C for carbon. The first letter is always capitalized. For example, H for hydrogen, capital H. If there is a second letter, it is lowercase. So for example, capital N, lowercase a for sodium. And so some of you are like, hey, why are these names, they don't match up with their symbols? Well, it's because the origin of some of these symbols are Latin, Greek, some are scientists' names, and some come from locations. All right, so we finished up our first page of notes. Just to double check, here are the blanks you should have. Again, a reminder, you can pause it if you need to correct yourself or if you missed some blanks, fill them in. All right, so we're on the next page now, on page 48, arrangement of the periodic table. So the period are the rows, so those are horizontal, they go from left to right. Each period has a new quantum shell, or just a new energy level of electrons. So you can figure out how many electron shells, energy levels, an atom has based on the row it's in, the horizontal. So for example, hydrogen, it's in the first row. So is helium. Those two are in the first row, they only have one energy level. If you move down to the second row, going from left to right, examples are lithium, beryllium, boron, carbon, nitrogen, oxygen. Those all have two. If you go down one more, sodium, magnesium, aluminum, those all have three energy levels. So let's look over here. Okay, these all have one energy level. If we're making a Bohr diagram, these all have 2, 3, 4, and so on and so on. Group or family, those are the columns, those are vertical. So our up and down, these are our families or our groups. Each group has a specific number of valence electrons. These are electrons in the outermost shell. So when we're making our Bohr diagrams, our valence electrons are just the ones in the last shell. So each group has a certain number of electrons in their outermost shell. So for example, let's do lithium. Lithium has an atomic number of 3. That means 2 go in the first energy level and 1 goes in the last energy level. Beryllium has 4 electrons. 2 go in the first energy level and 2 go in the last energy level. So its valence electron is 2. Then we could skip over to boron. That would be 3, 4, 5, 6, 7, 8. So this row would have a full valence electron. All right, classes of elements. Metals. So our metals are from lithium to aluminum, then diagonally down to the right. So let's look. So all these blue ones are metals. So as you can see, there's more metals on the periodic table than anything else. They've got a luster or a metallic shine to it. They're ductile, which means you can put it into wires, like a copper wire. They're malleable, which means you can bend them, right? You can bend that copper. Good conductors of heat and electricity. So when you touch it, it feels really hot, or they're good at connecting electricity. They're solid at room temperature, except for the one which is mercury, which is liquid at room temperature. So most of them are solid, like you have an iron bar or a gold block or a silver block. Those are all metals. So all the metals have similar properties. Now, here are 2 examples of metals. We have sodium and potassium. So this is sodium, this is potassium. So this row, remember, has 1 valence electron, so 1 electron in their outermost shell. And what they want to do is their goal is they want to fill up their valence shell, so they want to bond with other elements because they want to be full. When the outermost shell is full, it's stable. So because these guys, sodium and potassium, are unstable, they react with water. So let's see what happens. So just a piece of sodium in water. So an explosion and fire happens in water because the sodium has only 1 valence electron. Therefore, it's reactive. It wants to get a full valence electron, like up to 8, be completely full. But because it's not, it's reactive. Pretty cool. All right, so now potassium, if we go back, it's down below sodium, and it's even more reactive. So as you go down this column of this row, these metals get more and more reactive. So let's watch potassium in water. So this is just potassium in water.
If we continue down the column to potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily as we...
So it's a metal, and that's showing how malleable it is. It's moldable, it's able to be cut. And notice how it was stored in a gel so that it wouldn't react with water.
Expose the shiny metal surface underneath.
So it's got that luster, that shine.
The potassium is extremely soft. We can easily flatten out the potassium metal It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein.
All right, so you can see that the potassium was more explosive than the sodium. So just think about the explosion with the ones down here. Pretty cool, huh? All right, so here are some more examples. Copper, iron, aluminum, brass, steel, gold. Then on our periodic table, we have nonmetals. So if you go to hydrogen, skip over to boron, and then go diagonally down to antimony. Okay, so all of these guys. Nonmetals. So there's less nonmetals than metals. So their properties, they have no metallic luster, no shine. They're not good conductors of heat, electricity, and they're gases at room temperature, except for bromine, which is a liquid. So here are some examples. So we've got the deadly chlorine gas, oxygen gas, we've got nitrogen, carbon, phosphorus, sulfur. So inert gases, they are nonmetals, but they're a specific type of nonmetals. Inert gases are only this column. So even though we have nonmetals over here, these are nonmetals, but they're special. They're called inert gases. They don't bond with other elements because they have a full outer energy level of electrons. Their valence shell is full. So remember how I said sodium and potassium were really reactive? Because if you look at their Bohr diagram, they only have one electron in the outermost shell. They want to fill that up so it's full. So they like bonding and sharing electrons with other elements. However, these guys, their valence shell is already full. For example, neon. You have 2 in the first electron energy level and 8 in the second. 8, it's full. They don't want to share anymore. They don't want to bond. So therefore, they're inert. They're not reactive at all. So neon, like I just said, 2 in the first, and then they have 1, 2, 3, 4, 5, 6, 7, 8 in its outermost shell, making it a stable. Helium, same thing. It's got 2. So when you put a flame to a helium balloon, it doesn't go up in flames. If you put a flame next to a hydrogen balloon, it'll explode into a gassy fire. All right, so here's where you should be for the second page of notes. Pause if you need to. And then on the left-hand side on page 47, I want you to color in the metals. So these are all of our metals, most of the periodic table. You can choose whatever color you want, just be consistent that these are the metals. Write it down here. Then I'm coloring in my nonmetals. And then I want you to circle the inert gases, last column of metals. I'm sorry, the last column of nonmetals. They're also called noble gases. All right, and that concludes our notes for today. Be sure you can know that you can go back if you need to. Bye.